Hello everyone. This video is about the solution of Unit 3 IAL Physics of the January 2021 session. So let's begin. The first question is about finding the acceleration of a glider moving through an air track. So an air track is basically an instrument which helps us move the glider without facing much friction, because it pumps air throughout the sides, and that causes the glider to reach out its wings and move without facing friction from the track itself. So to find the acceleration, we need to make use of both the initial velocity and the final velocity, because the formula to find acceleration is v minus u by t. So we need the final velocity as well as the initial velocity and the time taken to travel between the two light gates. Why are we using light gates? Because light gates are instruments which pass a ray of light, and when the front of the glider touches the light of the light gate, that is when the interruption starts, and that's how the timer starts in the light gates data logger. And once the back of the glider has passed through the light gate, that is when the interruption stops, and that is when the timer in the data logger of the light gate stops. So this is applicable for both light gate 1 and light gate 2. So light gate 1 will give you the initial velocity, light gate 2 will give you the final velocity. And to find, we have found v and we have found u, and to find t is actually the time taken for the glider's front to cross both the light gates. So if we are considering the first light gate here and the second light gate here, and I'm considering the time it takes for the front of the glider to touch this first light gate, and then the front of the glider to touch the second light gate. So this time between the glider's front touching the first light gate and the second light gate, this time is the time that we are going to use here. Okay, so using this we are going to get the acceleration, and we have to repeat this experiment to get average values. That's the general rule of any experiment in physics or in chemistry or what in any form of science. You have to get repeat readings. You get more and more readings, you'll get a more average value, and you'll get a more accurate value. So that's what we did over here. So then we made use of these data to plot a graph of acceleration versus force. So it should be a straight line, and it's not going to be a straight line through the origin, because as we can see, it's not actually going through the origin 0. You have to make sure whenever you draw a line of best fit that it passes through as many points as possible. The line of best fit means it has to pass through as many points as possible. So it's not necessary that you have to pass through the first point. If the first point is hindering you in drawing a line of best fit, then skip it. Okay, just take the points which will allow you to draw a line of best fit passing to the most number of points. So the student concludes that these results do not show that the acceleration is directly proportional to force. Comment on the student's conclusion. The student is correct. Why? Because for something to be directly proportional to something else, the line has to be passing through the origin, and in this case we can see it doesn't pass through the origin, so it's not directly proportional. Describe how the students keep the total mass of the system constant during the investigation. They are telling us that the teacher explained that for the resultant force to be directly proportional to the acceleration, the total mass of the system must be kept constant. So now if we keep the total mass of the system means what? The masses of the slotted masses and the mass of the glider itself. So if we have to keep the addition of the forces, the mass of the glider and the mass of the slotted masses, if the total mass of these two things have to be kept constant, now how can we keep it constant and apply different forces? Because to apply different forces I have to increase the forces here by adding more masses, right? So if I have to keep the total mass constant, what can I do? Now if we wish to keep the total mass of the system the same, that means we cannot be adding more masses, because we have to keep the total system's mass, total mass of the system to be the same. So we cannot keep on adding more masses. That would ruin that possibility. So what we have to do is we have to basically take these masses from here and put them on top of the glider. That will mean that even though the glider's mass has increased, the total masses remain the same. So this is how we can apply different forces here by not changing the total mass. So we take the mass from here, place it on top of the glider. That would ensure that the total mass remains the same, and at the same time that would allow us to apply a different force from the pulley. So this is how we keep the total mass of the system constant, by not bringing anything else from the outside, but rather altering the places of the masses within the system itself. Number 2, this is basic critical angle question. So critical angle, whenever the incident ray is striking at the critical angle exactly, that is when the light will stay exactly on the surface. So this angle of incidence is actually equal to the critical angle, so we have to draw normal to show the position of the critical angle. That's the first part. Then the second part is finding the refractive index of the glass, or rather the transparent material. So if we want to find the refractive index, we have to use 1 by sine c, and we found the critical angle using a protractor which came to 38 degrees. So this is the answer we got. Then calculate the range of possible values of the refractive index. So here this is another semicircular block of a different transparent material, and the measured value of the critical angle was 41 plus minus 0.5. So it was either 41.5 or 40.5, right? So let's say we use 40.5 once, we use 41.5 once, and we will get two different values of refractive index. So it ranges from 1.509 up to 1.54. That's what I wrote. Then this one, deduce whether this block is made from the same material as in block B. So block B's refractive index was between 1.51 to 1.54. We have to find the refractive index of this one and see if it falls within this range. And as you can see, we used sin I by sin R, and it came to 1.53. That falls exactly within this range, 1.51 up to 1.54. That means this and this, they are made from exactly the same transparent material. Now the student uses ray of white light. Explain why using monochromatic light would increase the validity of the conclusion made in C. So in C, we found the refractive index. Now if we use in place of monochromatic means single color, mono means one, chromatic means light. So if we use a light of a single color, that would make the investigation easier. But if you use light of white light basically, when it passes through glass, it separates into 7 different colors. You will have 7 different rays passing through the glass once it separates, right? That would make things very difficult to measure individual refractive index, right? So because that would make our life much difficult, that's why I said that with white light, it would disperse into 7 colors, each with different paths. It would be very difficult to measure individual angles due to the different speeds. Monochromatic light contains light of one color, so it is easy to determine the angle of refraction. So if you wish to find the angle of refraction in an easy way, you go for monochromatic light. But if you go for white light, you have to find the refractive index of all the colors separately, because all the colors have different refractive index in glass. That's a problem. This is basically a spectrometer, and spectrometer is another device which is used to measure refractive index by measuring the value of the angles. So why is this one more preferable as compared to the protractor? Because in this one, the resolution is 0.1 degrees. I mean, it can measure up to 0.1 degrees, something as small as 0.1 degrees. But in this one, it can measure as whole numbers, right? 64, 36, or whole numbers, as you can see, no decimal places. So that's what I wrote here. Protractor measures to a resolution of only 1 degree, but while the vernier scale measures up to as less as 0.1 degrees. More precise values are obtained using vernier scale, reducing uncertainty. The collimator can create narrow parallel beams or refraction of light, resulting in lesser uncertainty. So they have written here that the light emerges from the collimator in narrow parallel beam. So if it's a parallel narrow beam, that means the lights are not interrupting or not interfering with one another. That means you'll be able to find the exact value of the angle of the different lights and their angles of refraction, right? So even if you pass white light through it, you can actually make use of it. In here, you can find the different colors, refractive indices more accurately using the spectrometer. But that would not have been the case using the protractor, because the white light's colors would not have been parallel, and they might have interrupted with one another. That would have made life very difficult to actually find individual refractive indices of the different colors of white light using protractor and the ray box. Next one, number 3, this is a force extension question. So this is for a rubber band. They are telling you to show a diagram as well. So you clamp it, use a clamp and a stand to clamp the rubber band, and then you place loads from the bottom of it to extend it. So first you have to take the length of the rubber band without any loads. That will give you the original length. How do you measure it? Using a meter rule. And then after you've placed the loads, you have to of course place the load by knowing the exact value of the load. You have to know the exact value of the load before applying it at the bottom of the rubber band. So the exact value of the load may be found using first you have to find the mass of the load using the electronic balance. Then you multiply that mass with value of G. That will give you the value of the load, okay, the weight of the load. And after you have applied that pre-measured load, the new length of the rubber band is measured using the meter rule, and then you subtract the old value of the length of the rubber band from the new value. That will give you the extension. So this is carried out for a range of different loads, and that is how you will get many values of the force and the extension, which are later used to draw graph. Okay, so that is what I wrote over here. So you have to make sure you are labeling everything as well as mentioning all the devices which are used to carry out the measurements. As you can see, electronic balance to measure the loads and the meter rule to measure the extension of the rubber band. So this is basically the hysteresis graph, which contains the loading and the unloading graphs together, and in between them, the area in between them is basically the hysteresis loss, which is lost to the system. So estimate the energy transfer to the internal energy of the store of the rubber band during the loading and unloading. So you have to find this area in between the two. So this is an estimation question, of course, because it's not a proper shape. So you have to estimate how many boxes there are within these, and as you can see, each rectangular box is actually equal to this much. Okay, so the length is 1 and the breadth is 0.05, so each box is equal to 0.05 joules. So since if you roughly count the number of boxes, there are approximately 17. There is a range, of course. Different people will get different number of boxes. So I got 17. So 17 multiplied by each box's value 0.05 comes to 0.85 joules. Okay, so this is question number 4. It makes use of an analog voltmeter, and you have to find the percentage uncertainty in finding the potential difference. So if we look carefully, if we zoom in, that it can measure as 9.5, 10, then 10.5, then 11, then 11.5, then 12. So it can make a mistake. The uncertainty is basically how much mistake there is possible. So that depends on the resolution of the instrument. So in here, the resolution of the instrument, if you look carefully, it is 0.5 volts. So we always take half of the resolution of the system. We always take half of the resolution of the device to get the uncertainty, because if it's at 9.5, it could a bit to the left or to the right. Let's say if it's a bit to the left, it could be 9.25. If it's a bit to the right, it could be 9.75. Right? These are the small mistakes which might happen if it's exactly at 9.5, because it could be a bit to the left, it could be a bit to the right. We don't know, right? It could be a bit to the left or it could be a bit to the right. So because there's that bit of uncertainty in whether it's actually 9.25 or with 9.75, it can be either in the negative range or in the positive range. So that is why whenever we find uncertainty using the resolution of the instrument, we have to pick half of the resolution. So if the resolution here is 0.5, we have to pick half of it, which is 0.25. That is how much mistake or how much uncertainty there is in finding the value of the voltage. So this is what we did. Percentage uncertainty is uncertainty divided by original value. Original value, as you can see here, it's pointing at 10.5. It 100%. That's what we got. Then this is a digital multimeter. Discuss the advantages of choosing the digital multimeter to measure the potential difference. So of course it doesn't have parallax error. You can make parallax error over here by looking at it not directly. Okay, that's one mistake that you can avoid using a multimeter. The second one is this one gives you readings up to 2 decimal places, while analog, as you can see, gives reading up to 2 decimal places, right? 2 decimal places. But the analog one, it doesn't give you readings up to 2 decimal places. It gives you reading up to only 1 decimal place. So that is a place of concern, which is not there in the multimeter. You can get a more precise value. So if you get a more precise value, the uncertainty is reduced. As a result, the percentage uncertainty is also reduced. So this is why the digital multimeter is more preferred. This is the last question. So in here, they're investigating how the temperature affects the resistance of the copper wire. So they have given a chart and criticized these results. As you can see in this chart, the number of temperature values is too low. Only 1, 2, 3, 4, 5, 6, only 6 values. So whenever you perform an experiment, you should take more and more values, 10 if possible. The other one is the temperature values need to be measured at regular intervals. It's here 22, then 33, then 38. There is no consistency, right? You have to measure the temperatures at consistent intervals, right? The other one is the resistance values are very haphazard. Here it's up to 2 decimal place, here 3 decimal place, here 3 decimals, here again 2 decimal place. So this shouldn't be the case. It should either be all 3 decimal places or all 2 decimal places, but not a mixture of both. Then using these values, we drew a graph of a line of best fit. And again, line of best fit means you have to make sure that the line passes through as many points as possible, right? Then this is the next part of the question. In here, they are telling us to find the value of alpha and R naught. So in this question, you are allowed to use 2 things. You can either use 2 sets of values, because here you have to find 2 unknowns, and whenever we have to find 2 unknowns in mathematics, we take 2 sets of values. So I took 2 sets of values from the graph. Okay, You can take this, the one I did, or you can apply y equal to mx plus c to find from the graph directly. So the graph, for the graph, the y is r and the x is t. So if we altered this equation, y equal to mx plus c, the m is basically alpha r naught, c is r naught, and the rest is y is r, x is t. So the y-intercept will give you r naught and the gradient will give you alpha into r naught. So from the y-intercept you can directly find the r naught and then you put it here, find the gradient, and from the gradient, after you found the gradient, you know r naught, you know the gradient, from there you can find alpha. So that's one way, or you can do the way I did using simultaneous equations. Both will give you the same result. Number D, the last part, explain one modification to this investigation that would improve the accuracy of the values of R naught and alpha. So like I said, if we go back to the chart, we can see that the values are very haphazard. We can take the values, at more regular intervals. That would allow us to get more values in between. We are not getting the in-between values, 22 and 33. There is nothing in between 22 and 33, right? We can get the in-between values. If we get the in-between or the intermediate values, we will have more values of temperature and resistance that will allow us to get a better graph with more points, and that will mean that the gradient value would be more accurate. If the gradient value is more accurate, that means we can find alpha and R naught more accurately. Okay, so these are the answers to this paper. Thanks for listening. Thanks for watching.